Okay. Hi everyone. I'll be giving a presentation on Tavis-Cummings Hamiltonian, which helps to solve this problem of an N interaction between an N molecule with a single mode radiation. So during my last presentation, I talked about the Tavis-Cummings Hamiltonians, which involves the interaction of one two-level system with a single mode radiation, and James Cummings was able to come up with a solution to the problem. So what Tavis did was to what Tavis is trying to do is to solve the problem caused by the interaction of N two-level system with a single mode quantized radiation. And why he's trying to do that is because most of our real life models are involved with not just one two-level system, but more than N two-level systems, such as the laser. So here he assumed that the system here the model is done in resonance, so there was no radiation loss due to interaction. And because of this ideal or perfect model, he was able to generate the solution, the exact solutions for the interaction of the Hamiltonian. And based on his research, what he did was to compare the the exact solutions for the problem with certain approximations also done by people, such as the average field approach and the modified two-level model approach. But based on this presentation, I will just be dealing on how he was able to formulate the problem and also solve the exact solution. Okay. So for him to develop this Hamiltonian, he used 3 methods to develop this Hamiltonian. First of all, he started with the general Hamiltonian, which we all know, or we passionately know as a semi-classical Hamiltonian. He was able to generate the semi-classical Hamiltonian, or the quantized Hamiltonian that was described by James Cummings Hamiltonian, and he further simplified it using and this is the general semi-classical or quantized Hamiltonian generated by James Cummings. And from this,
can you start from the beginning of your slide? You have 3 terms there. Can you just call what this notation means? HM, HF, HI.
Okay. So HM means the Hamiltonian of the molecule, HF the field, and HI the interaction. And this is the popular Hamiltonian, which this follows the potential energy plus the kinetic energy. And for our interaction, this was something we explained when we're talking about the light matter interactions.
Where A in this expression?
Yes.
A vector there. How you call it?
Vector potential. Vector potential.
Okay. The vector potential of the field, right?
Yes, vector potential of the field. Yes. So why this Hamiltonian is for the electric field, why he here is the electric field and H here for some reason was the magnetic field. I don't know why H was used, but I just went with it.
And C is speed of light or the distance?
Yes, speed of light.
Why not distance? C square.
Yes, it's the speed of light.
I think this distance is square.
No, it's just a square.
You wish to t square or something distance is square. Square of distance.
Like it should be not just 2mc square, it should be some other term in the denominator.
I think, it should be a square of the distance.
No. Dinesh is expecting to see dipole approximation, or distance between positive and negative charge is multiplied by electric field. And if you see, Patricia is showing it as an approximation as a last last line of this equation. But more general, doesn't have distance, it has only momentum and vector potential. Thank you for the question.
Okay, so this is the interaction when one two-level system interacts with a single mode radiation. So what if we have the interactions that involve multiple two-level systems interacting with a single mode radiations? This is what we have here. And after a series of gate transformations and dipole approximations that was not mentioned in the slides, they were able to arrive this equation. This equation looks similar to what James-Cummings and Hamiltonian gave us, except for the summations, where here is the electric field and here is the dipole moment. So if further simplified this term using the molecular and feed quantization, my bad, there were really a lot of calculations involved on how he was able to simplify from the previous equation to what we have here, which was not mentioned here. But after simplifications by different approximation, he was able to arrive at these Hamiltonians of the system, which involves this first two term is our unperturbed Hamiltonian, and this relates to our perturbed Hamiltonian, as stated here. So the eigenstates of the non-interactive system. So to formulate our problems, we first need to get the eigenstates of the non-interactive system. So the eigenstates of the non-interactive system was defined in this, where the eigenstates of this was this, for the unperturbed. And for this HAR3 is a bit confusing, but if you can imagine it as when we're doing our angular momentum, where we describe.
What is your R again?
Yes, that's what I'm trying to explain. Like our angular momentum, this HAR3, when we're describing in the first session of the class, when we're describing angular momentum, where we have Lx, Ly, Lz. So the HAR3 here represents like Lz. So it was just given as R3. Like R1, R2, R3. I think that was how Tavis explained his momentum is HAR3. So HAR3 can be similar to what we have as Lz. So
R is just the angular momentum.
Please explain in my words.
Yes.
So
It's just coordinates.
yes, the coordinates, yes. And
what is plus and minus then?
yes, the raising and lowering operator of the.
Okay. So it's laser operators based on the angular momentum.
Yes, this.
So let me help so that we progress quicker forward. System of n two-level systems, which are speed 1/2. One assumes that there is an addition of angular momentum of n speed 1/2 system, and then one gets is a overall system with n capital over 2 angular momentum. And for this combined system, one practices the projections of angular momentum and raising and lowering operators. So it is a basis to progress further.
Okay, thank you. So this is what I explained, that this state here are formally identical to the states that we have for the total angular momentum and the total z component of momentum for a system of spin. And the RM states are formed in the same way from single molecule states, spin up, spin down. So something I forgot to mention, because of commutation relationship, it was noticed that this Hamiltonian, this total Hamiltonian commutes with HO, H0 and R3, commutes with both of them. So we can say that they both have the same eigenstates. So, and because of that, we're able to get something like this. So to be able to construct this problem, we have to turn these states into a matrix where your dimensions are 2 raised to power n, where n is your number of two-level systems in the model. So what we have here this is a representation of a matrix where we have the diagonal that are non-zero elements. The diagonal are also splitted into smaller boxes, where they assist to.
A second, we will get only diagonal elements in this Hamiltonian?
Yes.
You just
Block diagonal.
block diagonals. Okay, so it means like what you mark is not a single element, it's a, I don't know, 2 by 2, 3 by 3 kind of small pieces.
Yes. Yes. So these elements. Yes. I think I do not get your question. Yes. I do not get your questions.
No,
There's no question.
Oh, okay.
I mean, you already answered.
What do you call blocks? We can call it block.
Oh, okay. Yes. Okay. So, and previously I said this for this 2 by 2 block matrix, we have some the diagonal elements are also splitted into smaller smaller blocks of matrices also, in which can be calculated using this formula, these formulas, and them having the dimensions of 2r plus 1. Sorry, this is error. So assuming that we have the state Rcj as the eigenstate of H2 H squared R3. Recalling we already have our in the previous slide our eigenstate to be this. So we are assuming that if you assume that our R cube our state is this. So this is also M, but your M is C minus n. So we are making the summation, our states, the summation of all the states here for n two-level systems. So there was a lot of math problems being solved that went from here to here, which I tried to understand how they were able to use some basic approximations and boundary conditions to define what went from here, how to define this and this. But from what Travis explained, it was able to confirm this problem and get your eigen problems to be this. While your an, sorry, this is an, is from here. So it's acceptable to define your eigenvectors as this. While your q is your eigenvalue. So the largest value of q for a given value of r and c corresponds to the ground state of the system, and for the ground state of the system.
What is your identical block equation? What was your identical block equation?
This?
Yeah, you said.
Yes, this represents this.
No.
That's what this is for me.
Yes.
For
Why you have kind of this, why your system returns to this kind of block-like Hamiltonian? Yes. What's the physical reason for this? Why it's not having everything spread with some coefficients?
Because they wanted to, it was trying to use a matrix to solve the eigenvector.
This would be easy to solve.
Yes,
it's really solve it block by block.
Yes.
But what's the physical reason results on making your Hamiltonian like this?
Because you can easily diagonalize the matrix to give you the eigenvectors and eigenvalue.
Okay, so can you repeat again, what is this n? What's the difference between n, m, r prime?
Yes, it's just different notations for your different notation, basis of different eigenstates. Is that what you're asking? Yes.
But what is the index m and r stays for?
I just assumed this.
Yeah, but just give them a name with human words.
States?
No,
Wave
no,
function?
Like total speed Z projection spin.
Okay, is that oh
So let's go back to your Hamiltonian. Yes. So R is total spin, M is magnetic projection, and
yeah. Oh yes, of
N
course.
is number of quanta in the field.
Yes.
Huh.
Yes. Okay. Yes, of course. Total spin, like the way we have in our angular momentum, total spin, then magnetic projections, and number of quanta.
And it looks like because you have these block elements, right? In other words, your quantum state of the field is coupled with some specific states. Most of the states are not coupled with electric fields. That's why you have zeros in a non-diagonal. Most of the non-diagonal elements are
Yes.
zeros
Yes.
because your field is not really coupled with everything.
Yes.
It couples with some specific elements with this specific angular momentums and specific spin position, spin number, right?
In brief, answer to your question is energy conservation.
Oh, okay.
So total number of quanta in the system doesn't change because it is isolated.
Isolated. Yes.
If electronic system in ground and photon is state number n, it can exchange only one photon and distribute over this and that states. So
Okay. Yes. Yes. Okay.
And in between only nearest
Yes. Yeah.
In sense of
states with the nearest angular momentum.
Yes, because this model was Travis make sure that this model was done in resonance. There was no radiation loss in this model. So, so to solve this problem, it started with this. To solve this problem,
recursion.
recursion.
Mhm.
Yes, to solve this recursion problem can be solved starting from this. I tried to see how it did it to be able to get the values for your AN, or realistically, I still don't. But I know it was able to arrive with AN to be this. The eigenvectors was solved to be this. And
What is atom?
what is what?
Atom. Atom.
So, oh, sorry, understand. Sorry.
Atom is different.
Sorry, it's just, this is just me. Sorry. If it's wrong, I think it's just me. I don't.
Probably meant to say that.
Okay. No.
It should be photon.
No. Understand. That was what I was trying to say. Understand, like. Okay, sorry. So the eigenvectors was solved as this, and we can use, if you recall this, in these wave functions that was brought up initially, where we have a plus the plus our wave functions, we can be able to impute this here and get our value for our eigenvectors. So if you visualize the graphical illustrations of the solution, as I said earlier, that AN shows AN as a function of n for several values of R, C, and J. So if J equals to 0, it means that we have our ground state, and you see this shows that J is in a ground state, and if J equals to 1 is our excited state, and J equals to 2R is the most highly excited state. This is a graphical illustration. So Dr. Killing asked me a question that
This is not in a printed version.
yes, sorry. Sorry, he asked me a question that what if that my two-level system, my n equals to 2 for my two-level system, how am I able to solve it? So I tried to look at it and say, okay, what approach am I going to use? So from my very limited knowledge, I decided to start from the matrix block, since that we have the dimensions to be 2 raised to the power n, and the 2 and our n means how many molecules of two-level systems we have. And I said, oh, since our dimension is 2, our n equals to 2. So for that means our dimensions are 4, and we can be able to solve for the elements in the diagonals using this formula that I explained earlier. And from that, we are able to assume that they were just two blocks in diagonal. based on the formula, assuming R equals to N over 2. So the Hamiltonian of the molecule interacting with a single mode using the molecular quantization. I use the molecular quantization explained by Tavis to say the summation of from J equals to 1 equals to 2. And I came up with this, and this is the dipole moment for the system electric field. And if I have like the units for this, I think I should be able to solve for the Hamiltonian of the interaction, and I could be able to get the eigenvalues of the system by knowing the coupling strength, which is your K. Your C mostly is the same as your R, and your lambda, which is your eigenvalue. So if we know the coupling strength, to be able to find the value of C. So, and the eigenvectors can also be solved using the formula I showed previously here.
You are writing this for 2 helium like atom, right?
Yes, two level system. So this is I don't know if this is correct, but I just did a lot of. Okay, thank you.
Okay, let's